Hello, in this video we'll be doing the energy calculations for an alpha decay. So we start with a parent nucleus which splits itself into the daughter nucleus and an alpha particle during an alpha decay. And the energy released during the alpha decay goes into the Ke of these two nuclei. Let's look at one specific alpha decay, the alpha decay of radon-222 to form polonium-218. If we are provided with the masses of all these nuclei, we can calculate the energy released during this alpha decay. Quite simply, just take the mass of the radon-222 and minus it with the mass of polonium-218 and the mass of helium-4. Because if you take the initial mass minus the total final mass, the decrease in mass corresponds to the energy lost by the system. So when you multiply with C squared, you get the energy released. So it turns out every alpha decay of radon-222 releases 5.603 mega electron volts of energy. Where does this energy go to? It goes into the Ke of the polonium-218 and the Ke of helium-4. Now let me ask you a question. If you compare the momentum of the helium-4 and the momentum of the polonium after the decay, which do you think is larger? What do you think? Does the alpha particle has the larger momentum, or should the daughter nucleus have the larger momentum? Nah, both of them should be the same, yeah? These two momentums should be equal but opposite. Why is that so? Because of PCOM. Before the decay, the total momentum was 0. So after the decay, the total momentum should also be 0. So in order for these two momentums to sum up to 0, they must have the same magnitude but opposite in direction. Now let's move on to work out the ratio of the Ke of the polonium to the Ke of the alpha particle. Now, do you know that besides half mv squared, the Ke can also be expressed as p squared over 2m? Because momentum is m times v. If you replace the momentum with mv, you can convince yourself that p squared over 2m is actually the same as half mv squared. So when you express the ratio of the Ke's this way, you can cancel away the two momentums cleanly because they have the same magnitude of momentum, right? So it turns out the ratio of the Ke is simply the ratio of the masses, but you have to swap the order, yeah? So it's clear that the Ke of the polonium is much smaller compared to the Ke of the alpha particle. To be exact, the alpha particle has 54.5 times the Ke of the polonium. Now let's use the modern method that you learned during your PSLE days. So the Ke of the alpha particle is 54.5 units, whereas the Ke of the polonium is 1 unit. So in total, we have 55.5 units, which corresponds to the total energy released during the alpha decay. So the alpha particle's Ke is 54.5 out of 55.5 of the total amount of Ke, which we have calculated to be 5.603 mega electron volts. So it turns out the alpha particle grabs the majority share of the energy released, leaving the polonium with only 0.10 mega electron volts of Ke. Now in hindsight, the result is actually very obvious. The scenario is exactly the same as the rifle and bullet scenario. The alpha particle is like the bullets that went zoom, right? And the daughter nucleus is like the recoiling rifle. They must have equal but opposite momentum, since the total momentum must remain at 0. Not only do the velocities follow the inverse mass ratio, even the Ke follows the inverse mass ratio. Since the daughter nucleus is always much heavier than the alpha particle always gets the lion's share of the energy released during an alpha decay. Alright, that's all. Ta-ta!